Hi, I'm Rob, and I'd like to welcome you to this video on large language models in the AI Engineering Hands-On playlist on the Cumulus Cycles channel. If you watched the intro video to the playlist, you'll recall that I mentioned the focus of this playlist is on providing you with hands-on demo videos which relate to working with AI systems, and not getting into a lot of theory. That being said, I think it's important to at least cover a high-level overview of what an LLM is and how it works before we start coding. So in this video, we'll start out with a few concepts on LLMs, then get hands-on with some demos. Also, I just want to mention that from this point forward in the playlist, I'll assume you have your dev environment configured and are ready to start building. If not, please watch the dev environment setup video before moving forward here. Okay, with all that out of the way, let's get started. So, at a high level, LLMs are AI systems designed to understand, generate, and manipulate human language. These models are trained on a vast corpus of text and use statistical patterns in the data to predict the most likely next word in the text. And that last part about predicting the most likely next word is important to understand. See, LLMs learn patterns from text, and from those patterns, they can predict the next mostly like word to come in a sentence to build a response to the user's query. So LLMs understand context, but they don't know facts, even though they appear to. The process flow of an LLM pipeline starts with text input, the user's query, then moves to tokenization and embedding of the input text, where tokens are the basic text units, the words and subwords from the text, and embeddings are dense numerical vectors that represent these tokens. So essentially, text becomes tokens, tokens are converted into numerical embeddings or vectors, and these vectors are fed into a transformer, which is a specific and highly influential type of neural network architecture, famous for its self-attention mechanism that allows it to weigh the importance of different words in a sequence. Transformers revolutionized natural language processing and drove the creation of LLMs like ChatGPT. Transformers aren't just a model, but a powerful framework enabling sequence-to-sequence tasks by processing entire sequences at once, unlike older recurrent neural networks, which used long short-term memory implementations. And after the transformer analyzes the input sequence, or tokens, it produces a probability distribution over the vocabulary or the next most likely token for the text output. Now, let's take a bit of a deeper dive. So, the first step in training an LLM is to feed a vast corpus of text into the LLM. Again, the LLM doesn't memorize the text, it simply learns patterns in the data. Next, the text is turned into tokens, numerical representations of the text input. And it's important to note that the tokens can be whole words, parts of words, stems, which are roots of words, such as run from the word running, or even punctuation. Then each token is converted into a numerical vector embedding. A key concept in LLMs is the transformer architecture, which we previously mentioned. And this architecture uses self-attention to learn the context of the words. So here in the sentence, the dog chased the ball because it was fast, the keyword it refers to the ball. The dog chased the ball because the ball's speed was fast. And after the LLM understands the context of the text, it makes a prediction of the next most likely word or token based on the learned pattern in the data. Now, let's shift our focus from the core LLM concepts to talk about the types of LLMs we have available to us, namely frontier models and open source models. Frontier models typically refer to the most advanced AI models currently available, such as the models from OpenAI, Google, and Anthropic, which I'm sure you're familiar with. Some key characteristics of frontier models are that they provide the strongest general reasoning and performance of currently available models. They're accessed via APIs. They may offer limited fine-tuning, but model parameters, or weights, remain closed, and they're updated by the model provider. On the other hand, open source models are publicly available. They can be downloaded and run on your local machine, and they allow for fine-tuning. If you watched the environment configuration video in the playlist, you saw that we were able to run an open source model on our machine using Ollama. This README provides a comparison of frontier and open source models, as well as some guidance on when to use each type if you're interested in reading it. There's a link to the repo in the description below. Now, before we move on to the demos in this video, we'll briefly discuss the OpenAI Chat Completions API, which allows you to talk to models in a chat-style format. So instead of sending a simple prompt string like, "Who are you?" you send a list of messages which represent a conversation between roles, such as the system role, the user role, and an assistant role. When you send the conversation messages along with the model you want to use, you'll receive a model-generated reply for the chat completion. Using the Chat Completions API allows for multi-turn conversations where you keep passing the previous messages to the model so it retains context, and it provides a cleaner structure than using long string concatenations. Looking at the roles, we see we have the system role, which sets the high-level behavior for the model. The user is the human or upstream process sending the query, and the assistant is what the model previously answered to retain context. Some options you could pass into the Chat Completions API are temperature, which controls the randomness of the response, max tokens, which indicates the length of the response, top P, also known as nucleus sampling, which controls the output diversity of the response by selecting from the small set of most probable tokens, and response formatting, such as JSON. The rest of this notebook provides additional information about the Chat Completions API if you're interested in reading through it. But with the information we've covered, we have enough of a high-level understanding of LLMs to take a look at the hands-on demos. Now, looking at the README in the demo folder, we see the prereqs required to run the demo notebooks. First, we'll open a terminal in the demo folder and run the UV command to create the virtual environment. If you didn't follow along with the development environment configuration video in the playlist and you're not sure if you have UV installed, just execute the UV version command. And if you see a version come back, you're all set. However, if you don't see a version, feel free to check out that config video, then come back here. Or if you're comfortable using a different package manager, feel free. But I highly recommend checking out UV when you have a chance. So I'll execute the UVVN command, passing it the version of Python I want to use in this virtual environment. And if we look over in the file listing in the demo folder, we see our VN folder. Now I'll execute the source command to activate the environment, which we can see on the right side of my terminal. Now if I do a UV pip list, we see I don't yet have any packages installed. So I'll go ahead and execute the UV pip install command, passing it the requirements text file, which we see here, to install the libraries required to run the notebooks. And if we run the pip list command again, we see our dependencies are installed. One other thing I want to mention is that to run the OpenAI demos, you'll need to create a .env file in the demo folder and add your OpenAPI key. To do that, you can simply rename the .env.example file and insert your key. Now, with setup complete, let's launch Jupyter Lab in the virtual environment. In this notebook, we're going to walk through a simplified LLM pipeline. We'll start with plain text, then convert that text into tokens, and finally into embeddings. As mentioned previously, these embeddings are numerical representations that allow models to understand meaning, compare similarity, and reason about language. The goal here isn't to build a full LLM, but to clearly understand how text becomes numbers and why that transformation is important. So here's what we're going to cover. First, we'll see how raw text is broken into tokens. Then we'll map those tokens to numbers. After that, we'll convert those numbers into embeddings. And finally, we'll visualize and compare those embeddings so we can see how meaning is captured mathematically. One point of clarification I want to make is that you'll often hear this process summarized: text goes to tokens and tokens go to embeddings. But internally, the pipeline's a little more detailed. So first, text is tokenized. Those tokens are then mapped to token IDs, and those IDs are converted into embedding vectors. these vectors are what the model actually processes. So in this notebook, we're focusing on this early part of the pipeline, how text becomes vectors. Okay, with all that out of the way, let's look at the first code cell in the notebook. Here, we're just importing our dependencies. We'll be using principal component analysis to reduce the dimensionality of our embeddings so we can visualize high-dimensional sentence vectors in 2D or 3D space while preserving as much of their variance as possible. We'll use Sentence Transformer to generate dense vector embeddings for our text. These embeddings capture the semantic meaning of sentences, allowing us to compare, cluster, and visualize them based on meaning rather than just keywords. And we'll use Auto Tokenizer to convert raw text into tokenized inputs that transformer models can understand. Next, we'll define our text input, which is a list of 3 strings, with the first 2 being more closely related than the last. Now we'll load the tokenizer. We're using Distilbert, which is a light version of BERT. It was trained using knowledge distillation, which is a technique where a small model, the student, learns from a larger model, the teacher. It retains about 97% of BERT's performance while being 40% smaller and 60% faster, making it highly effective for NLP tasks such as text classification, sentiment analysis, and question and answering. The Distilbert-based uncased model is uncased, meaning it treats the word English with a capital E and English with a lowercase e as the same word. Again, we have a note on the technical accuracy of the LLM pipeline. And now we'll generate the tokens. First, we'll get the tokens by calling the tokenize method on the tokenizer, then the token IDs by calling encode, and then the token IDs without special tokens. And here are the results. We see there are 7 words in the text made up of 58 characters. There are 10 tokens with special characters and 8 without. And here are the tokens with their IDs. Now let's visualize the tokens. I'm not going to go through the code in a cell because the point is really to see how the tokens relate to one another. And here we see that the special characters are closely related in vector space, as are tokens for the words is and. Machine, learning, and complex are more closely related than when comparing to unfortunately and fascinating. Now let's look at the embeddings. So embeddings are dense numerical vectors which represent text in a high dimensional space, where each dimension captures some aspect of meaning and semantic similarity between the texts. Here we're using the all mini LM L6v2 sentence transformer to convert the text samples into 384 dimensional vectors. All mini LM LXV2 is a popular deep learning model from Microsoft used for creating dense vector embeddings of sentences or paragraphs. So let's run this cell to load the model, then the next cell to generate the embeddings, which we see here. In the next cell, we'll use cosine similarity to measure how similar the vectors are, which we see here. But the next cell provides a heat map, which will be easier to visualize. Before we move on though, note that the values closer to 1 are semantically related, whereas values closer to 0 are dissimilar. Now looking at the heat map, we see the first text with ML and the second text with AI are more similar than when compared to the text weather. Now let's visualize the embedding vector structure of the 384 dimensions. And as we see, the plots for text 1 and text 2 are more similar than the line for text 3. Finally, let's use PCA to reduce the 384 dimensional embeddings to view in 3D. So in LLMs, PCA is a dimensionality reduction and machine learning method used to simplify a large data set into a smaller set while still maintaining significant patterns and trends. which we see here. Now, the next notebook we'll look at will demonstrate how to use the OpenAI Chat Completions API. As previously mentioned, the Chat Completions API is a message-based interface for building conversational AI. It supports multi-turn conversations, role-based messages, and flexible interactions between the client and the LLM. Before we get started with the demos, I want to point out that in the prereq section, you'll notice that an OpenAI API key is required to make calls to the OpenAI models. And you'll need to put this key in a .env file in the demo directory. You can copy the .env.example file and rename it, then update with your API key. If you don't yet have an API key, head over to platform.openai.com, click Get Started, then create an account and follow the directions to create the API key. Okay, with the API key set, we can move on and import the required libraries. Here, you'll notice that we're importing OpenAI and .env. These are required to initialize the OpenAI client and securely load our API key from the environment variables rather than hard-coding sensitive creds directly in a notebook. Then we check for an OpenAI API key, and if we have one set, we'll initialize the client. So let's go ahead and run the code in this cell. Then scroll down and use the Chat Completions API to send a single message to the LLM. So here on the client, we're calling chat.completions.create, setting the model to, in this case, GPT-4o mini, and the message is a list of dictionaries with a role set to user and a content set to our query, which obviously in this case is what is machine learning. When the response comes back from calling create on the Chat Completions API, we'll store it in the response variable and then we'll print it. So let's go ahead and run the code in this cell. And we see the entire response. And we can also reference the message content on the first choice in the response. Next, let's add a system role to the Chat Completions create call. Here, we're still setting the model, and we have a list of messages. However, this time we see the first message has a role of system, which sets the high-level behavior of the model, like the assistant's tone and style. The content for the system role instructs the model to act as a helpful assistant that explains technical concepts in simple terms. So if we run the code in this cell, and look at the response, we'll see it's more concise than the earlier response we received when we didn't add a system role. Now let's take a look at multi-turn conversation, which builds a conversation by including previous messages. So here we're defining a list of messages, again setting a system role with its content, and for the user role's content, we're asking the LLM to write a simple non-recursive Python function to calculate factorial. So we'll call create on the Chat Completions API, get the response for the same model, passing the messages, then get the message content from the first choice, and we'll print that response. Then we'll append to the messages list a new role of type assistant and set the content equal to the assistant message, which was the response content we got back from the first call. Then we'll also append to messages a new content of can you make it recursive for the user's role. And in this case, it refers to the simple non-recursive Python function to create factorial. Then we'll make the request and print that response. So let's go ahead and run the code in the first cell. And we're provided with a simple non-recursive Python function to calculate the factorial of a non-negative integer. Then if we scroll down and run the code in this cell, The model responds with, certainly, it can make it recursive, and provides a recursive implementation of the factorial function, as we see here. The next cell simply performs a model comparison by populating a models list with the models we want to compare results from, then passes the same parameters to the create call and prints the results, as we see here. The next two cells pass values for the temperature parameter in the create call. The temperature defines the creativity or randomness of the model's response. A lower value instructs the model to be more realistic, whereas a higher temperature allows for a more creative response. So let's ask ChatGPT 4o Mini to write a haiku about coding, with temp set to 0. Then temp set to 1. I do see a slight difference in deterministic and randomness of the responses, but I'll leave that one up to you to decide. We could set the max token parameter to limit the length of the response. In the first cell, we ask the model to explain the history of Python. And we get a lengthy response back, even though we're only displaying the first 200 characters. In the second cell, we limit the response to 50 tokens. This next example demonstrates setting the response format property when we call the model. We're setting the content of the system role to tell the model that you are a helpful assistant that returns data in JSON format. And for the user role, we're passing the content of extract the following information as JSON, in which we're asking for the name, age, and city for the person with this data. So let's go ahead and run this cell. And we see the response is in JSON. And for the last example in this notebook, we'll use chain of thought prompting to instruct the model to show the work it performed, or its reasoning, to determine a response to our query. So here in the user roles message content, we're passing the problem, which is a store has 15 apples. They sell 3 apples in the morning and 4 apples in the afternoon. Then they receive a delivery of 10 more apples. How many apples do they have at the end of the day? Then we're asking the model to think through this problem step by step, showing your reasoning before giving the final answer. And if we run the code in this cell, we see the model breaks down the problem step by step and then returns the final answer. In the next cell, we're passing a logic puzzle of 3 friends, Alice, Bob, and Charlie, are standing in a line. Alice is not at the front, Bob is not at the back, Charlie is not in the middle. What is the order of the 3 friends from front to back? So when we pass this message, we're setting the content of the system role to you are a logical reasoning assistant. Always show your step-by-step reasoning process before providing your answer. Then for the user roles content, we pass the logic puzzle. And if we run the cell, again, we see the chain of thought the model went through to produce the result. Now, the last notebook in this demo shows how to use the OpenAI Chat Completions API format with Ollama. Of course, to follow along with this, you'll need Ollama installed, which we covered in the dev environment config video in the playlist. So after ensuring Ollama is running, we'll import Ollama into the notebook, then make a basic chat request to Llama 3.2 using the Ollama chat request format. Now, this may take a while for it to initially run on your machine if it needs to pull down the Llama 3.2 3 billion model. We can also add a system message to the Ollama chat request. As you see here, we're setting the content of the system role to you are a helpful assistant that explains technical concepts in simple terms. And we're setting the content of the user role to what is machine learning. And we see the response. When implementing multi-turn conversation with Llama Chat, we send the first request with the message containing the system and user roles. Then we'll set the value of the assistant message variable equal to the response message's content, and then append the content for the assistant role with the value of the assistant message. So let's go ahead and run this. Which we see here is a Python function for calculating factorial with a simple loop. Then in the second request, we'll append to the messages for the user role's content, can you make it recursive? And send the request. And now we see the response with the recursive function. Here we have two examples of setting the temperature parameter in Llama Chat, the first with a temperature of 0, and the second with a temperature of 1. Again, I'll let you make the decision based on the responses. So now that we looked at the OpenAI Chat Completions API format in the prior notebook and the Llama Chat format above, we need to ask why we would use the OpenAI Chat Completions API with Llama. And the short answer is because it gives us a standard, future-proof way to structure prompts and conversations, even when you're not calling OpenAI directly. As we saw, the Chat Completions format uses structured roles of system, user, and assistant. This gives you clear separation of instructions, the system, user input, assistant responses, and supports multi-turn conversation history, which matches how most modern instruction-tuned models, including those on Llama, are trained with chat-style data. So the bottom line is you should use the Chat Completions API format with Llama because it standardizes your prompts, makes your app portable, it improves prompt control, it matches model training, and it simplifies conversation management. Now, let's look at an example of using the OpenAI Chat Completions API format with Llama. And really, the big thing to point out is that unlike using the Chat Completions API with OpenAI, and we set the OpenAPI key in the .env file, the API key isn't really required with Llama. Well, that is to say you don't need a valid API key, you just need to populate the API key property with some text, as we see here. And we need to set the base URL of the local running Llama server. On this line, I'm setting an OpenAI format available variable equal to false because we don't yet know if Llama's OpenAI compatible endpoint is reachable. But if we successfully create a client, we'll set the value to true. So I'll go ahead and run the code in a cell. And we see we successfully connected to Llama's OpenAI compatible endpoint. Then going forward, I'll just check to see if the endpoint is available before making a request to the Chat Completions API. Now, here's an example of using the Chat Completions API format to call Llama. First, we'll set the model to Llama 3.23b or any Llama supported model, then set the user roles content equal to the query. Then we'll call create and print the response as well as the tokens. So let's go ahead and run the code in a cell. And we see the result. And that's it. So below are additional demos, which we saw in the prior notebook. They just call Llama models. So I'll let you walk through them yourself because they're pretty straightforward. So that concludes this demo on LLMs in the AI engineering playlist. If you found it useful, feel free to give it a like. And if you'd like to be notified when I add more content, please consider subscribing. Thanks for watching, and I hope to see you in the next video where we'll implement what we just learned in an actual application.